What slipped past our sun in 2017 wasn't a comet we recognized, nor an asteroid we could easily name. Tonight, on The Galaxy Scientist, we drift toward the quiet mystery of Oumuamua, a thin, tumbling visitor from another star whose motion and brightness changed in ways our models couldn't neatly explain. It came without warning, crossed our system like a muted spark, and left us with questions that still glow softly at the edges of astronomy. If this gentle wandering feels right to you, a soft like and quiet subscribe. Help others find their way here. For now, settle in, and we'll follow its fading trail, unhurried and warm. For a little while, astronomers found themselves asking a very simple question. What was that? A silent traveler from another star, seen only briefly in the soft window of October of the year 2017. It slipped through our neighborhood almost shyly, and yet everything about it felt strange. It hurried past at nearly 54 meters every second, a quiet rush through sunlight, while its brightness rose and fell in a rhythm that changed by roughly 66-1, as if it were turning the most unlikely face toward us, then away again. Its surface glowed in a deep, muted red, the sort of color that comes from being sandblasted by cosmic rays for billions of years. And still, as it passed, it left nothing trailing in its wake. No veil of dust, no ghostly gas, only a clean, empty path through space. Years later, in the year 2023, careful laboratory experiments suggested an answer to one of its strangest tricks. The tiny extra push in its motion, the acceleration that did not fit simple gravity, might have come from hydrogen slowly leaking out from within. Not a dramatic plume, but a whisper of gas, forming a thin, invisible stream that no telescope on Earth could see, yet acting like the gentlest of rocket engines. Imagine a football field made of ice and stone, nudged onward by jets so faint they never shine. Just push. It is a delicate thought, almost like picturing breath moving a feather in the dark. While scientists were still puzzling over the data, another idea began to take shape. This time, not about what the object was, but about what we might do in response. A quiet group of researchers refined a mission concept, tracing possible paths through space like threads on a map, and testing propulsion schemes that would squeeze every bit of speed from sunlight and gravity. Their dream is both simple and wild: to send a spacecraft to chase this ghost. If all goes well, a mission leaving in the late 2020s could slowly, patiently work its way outward, aiming to catch up with the traveler by the year 2050. The universe dropped a riddle into our sky, and humanity, small and stubborn, answered with a plan. To understand why this object stirred so much wonder, it helps to drift back to the night we first noticed it. In the year 2017, something unlike anything seen before swept through the inner regions of our solar system. On a clear night in mid-October, the Pan-STARRS 1 telescope in Hawaii, a patient guardian watching the sky, picked up a faint, moving point of light. That first detection came on October 19th, a date that would quietly anchor itself in the story of modern astronomy. At first glance, the object seemed like so many others that drift in from the icy edges, a likely comet. It was given a formal label, something like C, the year 2017, U1, a name more like a filing number than a story. But there was a problem. Comets usually arrive wrapped in a hazy envelope called a coma, a fuzzy glow born from ice turning into gas, often trailing a tail behind them like a streak of breath in winter air. This newcomer had none of that softness. No blur, no tail, just a sharp, star-like point. Within days, astronomers were forced to admit that their first guess was wrong. The object was renamed as an asteroid, with a new designation, A, the year 2017, U-1. Even that, however, did not last. As the measurements improved and the orbit was calculated more precisely, something extraordinary emerged. The path of the object was not an oval curve that looped gently around the sun, as planets and comets usually do. It was hyperbolic, an open curve that does not close on itself, the mathematical equivalent of a one-way road. The object was not only passing through, it was escaping. It was not held by the sun's gravity. It came from beyond our solar system and would never return. Faced with something so new, astronomers did what humans often do with a first-of-its-kind visitor. They made a new category for it. The object became known as the first confirmed interstellar visitor, and it received a more poetic name rooted in the Hawaiian language. They called it Oumuamua, a word that can be translated as a messenger from afar arriving first. The name honors both the place where it was discovered and the sense that this object was a kind of scout from the wider galaxy, the first of its kind that we had the good fortune to see. From the very beginning, Oumuamua refused to be ordinary. Its speed, its path, the way it swept in from the outer dark and headed back out on a hyperbolic trajectory, all pointed to a birth somewhere outside our own solar system. At its closest, it dipped inside the orbit of Mercury, rushing through the realm of the inner planets, while the sun's gravity bent its course, like a stone skipping near a whirlpool and then flinging back out into calm water. Around that closest approach, it moved at roughly 54 meters each second, a steady, silent plunge through blazing light before turning again toward the cold between the stars. Because it was only bright enough to see for a few short weeks, telescopes all around the world had to hurry. Night after night, observatories pointed their mirrors at the tiny traveler, gathering every photon they could before it faded. As they watched, they noticed that its light did not remain constant. Instead, it waxed and waned in a steady pattern, the way the brightness of a spinning object changes as it shows different sides. The shift in brightness was dramatic, far larger than what you would expect from a roughly round body. This suggested that Oumuamua was not a simple sphere, but something remarkably stretched or flattened. Early estimates painted it as a cosmic cigar, perhaps up to 440 yards long, with a length about 10 times its width. That image captured many imaginations. A reddish spindle turning slowly in the night, a needle sliding past the sundial. Later, as astronomers studied the detailed rise and fall of its brightness, they realized there might be another possibility. Instead of a cigar, it could be more like a flattened disc, a kind of cosmic pancake, with proportions where its broad face was several times wider than its thickness. Whether cigar or pancake, what mattered was that it did not look like any asteroid or comet we had catalogued before. Its size, too, made it easy to miss and fleeting to study. Oumuamua was only a few hundred feet across, small on the scale of the solar system, and its color was a dark, deep red. That kind of shade is often seen on bodies that have spent countless ages exposed to high-energy particles, their surfaces slowly darkened and hardened by cosmic rays. You can imagine it as a traveler whose coat has been bleached and scarred by endless storms, every patch of its surface holding a quiet record of the places it has passed through. One of the most unsettling details, though, was not how it looked, but what it failed to do. When icy objects like comets swing close to the sun, they usually flare with activity. Ice buried beneath their surfaces warms, turns into gas, and escapes into space, forming those familiar glowing comas and tails. Yet, even under deep, careful observation, as Oumuamua passed by, there was, as one astronomer described it, not even the faintest hint of dust or gas around it. It remained stubbornly clean, a bare rock or slab sailing through intense sunlight, as if nothing beneath its surface were melting at all. And still, as it left, its path betrayed a secret. When scientists compared the object's motion to what pure gravity would predict, they found a small but definite mismatch. Oumuamua was accelerating in a way that could not be explained simply by the pull of the sun and planets. It was as if something were giving it a gentle push from behind, a tiny extra shove that nudged it ever so slightly off the expected course. For typical comets, this kind of non-gravitational acceleration is normal. The jets of gas that escape as ice warms can act like natural thrusters, but in this case, no jets were seen, no cloud, no tail, nothing that should have produced such a push. This was the heart of the puzzle. An object that behaved like a comet in its motion, but looked like an asteroid in its appearance. Acceleration without an engine, a push with no visible hand. Was there something being released that our instruments were simply unable to catch? Or was the object itself stranger than any fragment of rock or ice we expected from nature? Outside the scientific community, popular media leaped on the mystery, spinning tales about alien probes and disguised spacecraft, using the silence around the object as a canvas for every imagination. Inside observatories and offices, however, most astronomers stayed with quieter, natural explanations, even as they admitted that none of the familiar categories fit well. For a while, we were left with a kind of cosmic ghost story, an interstellar visitor, seen once, already fading into the outer dark, leaving behind only numbers and questions. In the year 2020, two researchers, Daryl Seligman and Gregory Laughlin, offered a bold idea to soften that mystery. They suggested that Oumuamua might not be made of ordinary rock or common ice at all, but of something far more delicate, molecular hydrogen ice. In simple terms, they imagined it as a kind of hydrogen iceberg, forged in the bitter cold of a giant molecular cloud, one of those vast regions where gas and dust gather between the stars. In such a place, temperatures can fall so low that even hydrogen, which usually exists as an invisible gas, could freeze into solid form. Over long stretches of time, chunks of this frozen hydrogen might break away, drift through space, and eventually find their way into other star systems. If Oumuamua were one of these fragments, much of its mass could be made of molecules of hydrogen, each molecule composed of two hydrogen atoms packed tightly together in ice. As this hydrogen iceberg approached the sun, the gentle flood of sunlight would begin to work on it. Hydrogen ice does not need to grow warm in the way water ice does. Even at extremely low temperatures, it can slowly turn directly from solid to gas, a process called sublimation. That means that without any dramatic outburst, hydrogen could quietly seep from the surface and just below the surface, drifting away into space. This smooth, even release of hydrogen gas could, the scientists suggested, act like a network of tiny thrusters scattered across the object's skin. Each escaping molecule would push back on the iceberg by a minuscule amount, and when you add up countless such pushes across its surface, you get a small but noticeable acceleration. Because hydrogen gas is almost completely invisible in the wavelengths astronomers were using, it would not form a glowing tail or a bright spectral signature. To our telescopes, there would be no visible jet at all, only the motion of the object itself, quietly betraying that something was at work. In this picture, Oumuamua behaves like a comet, outgassing, accelerating, responding to sunlight, while still appearing almost naked, bare, and asteroidal in every image. The hydrogen iceberg hypothesis wrapped two of the biggest mysteries into a single gentle explanation: the absence of any visible coma and the presence of that faint, non-gravitational acceleration that made it seem, for a moment, as though the messenger from afar was being pushed by an unseen hand. The hydrogen ice idea did more than explain a gentle push with no visible engine. It also painted a picture of how this strange traveler might have been shaped and where it could have been born. In their work, Darrell Seligman and Gregory Laughlin pointed out that if hydrogen were quietly turning from solid to gas and leaking away, the object would be losing mass in a very uneven, time-layered way. Over long stretches, that kind of erosion could carve and stretch a body, shaving off material here, thinning it there, gradually exaggerating its proportions. A once more ordinary lump of ice could be pulled into something far more extreme, a spindle or a flattened shard, sculpted not by chisel, but by the patient breath of sublimating hydrogen. They also looked at the kind of cradle that such a hydrogen iceberg would need. Hydrogen only freezes in unimaginably cold conditions, in places where temperatures hover just a few degrees above absolute zero, around 3 Kelvin. Those conditions are not found near stars, but deep inside the hearts of dark molecular clouds, those thick, shadowed regions of gas and dust that drift between the stars. In those cores, sunlight is blocked, starlight is muted, and the cold is so intense that even a gas as light and shy as hydrogen can settle into solid form. If Oumuamua truly was such a fragment, then its story would stretch far beyond our Sunday. It might have formed in one of those dense, frigid cores, packed among collapsing knots of gas that would one day give rise to new stars and planets. At some point, a gravitational nudge or a collision could have kicked it free, sending it wandering into interstellar space. There, for hundreds of millions of years, it could have drifted through darkness, its hydrogen ice slowly worn down by cosmic rays, its surface reddened and toughened, until, by a long chain of accidents, it happened to pass through our small neighborhood and briefly cross our view. Seen this way, the object became something almost poetic, a pristine iceberg from the frozen depths between stars, a relic from a place so cold and quiet that it felt more like a dream than a landscape. It was a captivating image, and for a while, many people found comfort in it. The mystery of the hidden engine seemed tamed, wrapped into a story of exotic ice and ancient journeys. But in science, even the most beautiful stories have to survive a colder test. The hydrogen iceberg proposal sparked a lively debate. Later that same year, another team, including Team Huang and Avi Loeb, took a closer look at the numbers and the environment such an object would have to endure. Their critique gently, but firmly, tugged on the loose threads. The first issue they raised was simple and unforgiving: heat. Not the fierce heat of a star up close, but the faint, persistent glow of the galaxy itself. Even in the deep spaces between suns, there is always some background starlight. Huang and Loeb showed that this diffuse light would, over time, warm a block of hydrogen ice, not to the point of melting in the everyday sense, but enough to make the hydrogen slowly evaporate away. When they ran the calculations, the results were stark. An object the size of Oumuamua, made mostly of solid hydrogen, would not last forever in the galactic sea. Bit by bit, starlight would chip away at it. According to their estimates, such a body would completely evaporate in less than 10 million years. That might sound long on a human scale, but in the life of the galaxy, it is a brief sigh. The trouble is that the motion of Oumuamua, its kinematics, hints at an age far greater than that. From the way it was moving when we first saw it, from its speed and direction, astronomers inferred that it could easily have been traveling for something like 100 million years or more, perhaps wandering from one region of the galaxy to another over and over again. That is many times longer than a fragile hydrogen iceberg could survive under the constant, whispering warmth of starlight. Hoang and Loeb also pointed to another difficulty: the journey out of its birthplace. If the object really formed in the dense, cold core of a molecular cloud, it would have had to pass through that cloud as it escaped. There, the gas and dust are thick compared to the thinness of regular interstellar space. Every collision with a dust grain or gas particle would stir energy into the hydrogen ice, making it evaporate even faster. Instead of preserving the iceberg, the very environment that allowed it to form would also act as a kind of grinder, eroding it as it tried to leave. Perhaps their most subtle but powerful concern was about formation itself. To build a macroscopic chunk of solid hydrogen, you need tiny seeds of hydrogen ice to grow and merge. Yet those embryonic grains would be fragile and vulnerable. Even a small amount of heating, whether from starlight, nearby forming stars, or other energetic processes, could warm them just enough for the hydrogen to return to gas and disperse. Getting from minuscule grains to a single, cohesive iceberg large enough to match Oumuamua seemed, in their view, extremely unlikely. When they put all these points together, their conclusion was clear and almost gentle in its firmness. A pure hydrogen iceberg, drifting for tens of millions of years or more, was not a realistic candidate. Long before reaching our solar system, it would have evaporated away, like a snowflake trying to cross a lukewarm room, vanishing into nothingness while its story was still beginning. This kind of back and forth can sound harsh from the outside, but it is actually one of the quiet strengths of science. One person or one team offers a hypothesis, another looks closely, prods at its edges, and checks whether it can withstand all the pressures of reality. Hypothesis and rebuttal, idea and correction, step toward and step back, all slowly nudging our understanding a little closer to something solid. The hydrogen iceberg was a beautiful picture, but it seemed increasingly fragile under the weight of these arguments. So the question remained, as soft and persistent as ever. If the object was not made of exotic hydrogen ice, then what was it? It still accelerated as if propelled by some escaping gas, and yet it still showed no visible coma, no streaming dust. The riddle had lost one possible answer, but the clues had not changed. After several years of thinking, rethinking, and reanalyzing the observations, a new explanation emerged in the year 2023 that felt, to many experts, both less exotic and more satisfying. Chemist Jennifer Bergner, together with the returning collaborator Daryl Seligman, proposed a gentler idea. In their view, Oumuamua did not need to be an iceberg made of pure hydrogen at all. It could be something far more familiar, an ordinary, water-ice-rich object, much like a typical cometary fragment that had simply been altered by the long, patient work of time and radiation. In this picture, you can imagine Oumuamua beginning its life much as countless comet nuclei do, a roughly irregular piece of rock and ice, rich in frozen water and other simple molecules. Then, instead of spending its whole existence orbiting a single star, it is flung out into the wide between-star darkness. There, over millions and millions of years, It is bathed in cosmic rays, those high-energy particles that rush through the galaxy at nearly the speed of light. Cosmic rays are small in size, but large in effect. They can penetrate deeply into ice, far below the surface, and their energy can break chemical bonds. Bergner and Seligman looked at laboratory experiments in which water ice is irradiated in a similar way. Those studies show that some of the ice does not simply sit there unchanged. Under the impact of high-energy particles, a portion of the water molecules split and rearrange, and new species form. One of those products is molecular hydrogen, pairs of hydrogen atoms that may become trapped within the ice itself. Over long spans of time, this process can build up a reservoir of hydrogen inside the object, not in one big bubble, but in many tiny pockets scattered throughout the amorphous ice. The hydrogen is trapped, held in place by the cold and the structure of the ice, like countless small sighs frozen in the body of the comet. The longer the object drifts through space, the more of this hidden hydrogen it can accumulate. Fast forward to the moment it enters our inner solar system for the first time. When Oumuamua approaches the Sun in the year 2017, it begins to warm, but only gently. Its surface does not reach temperatures high enough to dramatically melt water ice. And indeed, no water vapor is detected by our instruments. It remains, to our telescopes, dry and quiet. Yet, that mild warming is not meaningless. As the temperature rises just a little, the structure of the ice can begin to change. Bergner and Seligman invoked a process called annealing. In simple terms, it means that the previously disordered, amorphous ice starts to reorganize into a more ordered structure. As the lattice of ice rearranges, the tiny pockets that once trapped hydrogen can open, merge, or shift, allowing the stored gas to find pathways to the surface. In this scenario, sunlight acts not as a flame, but as a key. It unlocks the hydrogen that cosmic rays have been building up for eons. The gas then seeps out, not in dramatic geysers, but in a slow, steady release across the surface. That release is enough to create a gentle thrust, pushing the object along its path in a way that adds just the right amount of non-gravitational acceleration to match what astronomers observed. When Bergner and Seligman ran the numbers, they found that they did not need torrents of gas to make the effect work. The release of tens to perhaps hundreds of grams of hydrogen each second, spread out over the surface, would be sufficient. That is a small amount on human scales, about what you might think of as a handful of water in mass, emerging each second from a body hundreds of feet across. Over time, though, even that modest flow adds up, nudging the object onto a slightly different course. Because hydrogen is so light and so simple, it does not leave a bright mark. It does not form a glowing tail in visible light like the heavier molecules in typical comet comas. It does not reflect much, and it does not produce strong, easily detectable spectral lines in the optical range. Any dust mixed into the ice would mostly remain behind, held by the structure of the nucleus, rather than being swept away. The result is a kind of invisible propulsion, thrust without sparkle, motion without a visible jet. It is a quietly elegant idea. Ordinary water ice, plus the relentless touch of cosmic rays, gives you a body laced with trapped hydrogen. A modest dose of solar warmth then frees that hydrogen and turns it into a set of invisible, natural thrusters. Nothing exotic is required. No ultra-rare materials. No perfect formation conditions in nearly impossible environments. Just the familiar ingredients of comets and the long patience of space. What makes this model especially appealing is how neatly it lines up with what we actually saw. Oumuamua's surface appears reddish, consistent with a typical cometary object that has been weathered by radiation. There was no strong signature of water vapor or other common comet gases, matching the idea that the water ice itself never reached high enough temperatures to erupt violently. The object was small, as we know, and the level of acceleration derived from observations fits comfortably within the range that a modest hydrogen outflow could produce. In this view, Oumuamua is not a fantastical iceberg made of pure hydrogen, nor a piece of alien engineering coasting silently between stars. It is, instead, a very comet-like object that has simply spent an exceptionally long time in an interstellar deep freeze, building up a hidden charge of hydrogen in its icy core. When sunlight finally reached it in just the right way, that hidden store was released, and for a brief moment, the comet behaved as though it were wearing a disguise, moving like an active body while looking from the outside, oddly barren. Bergner and Seligman's explanation has drawn many scientists toward it, precisely because of this quiet simplicity. It takes the strange behavior of the object and places it within the realm of things we already know can happen, just combined in a slightly unusual order. It does not ask us to abandon the familiar tools of physics or to leap to extraordinary technologies. Instead, it reminds us how rich even ordinary ice can become when given enough time and enough cosmic weathering. After all the headlines, the speculation, the whispers about probes and beacons and alien sails, the truth may be far softer. Perhaps the answer to the question of what this visitor was is simply this: a particular fragment of comet shaped by ages of deep space that happened to carry a hidden reservoir of hydrogen and, in doing so, reminded us not to judge a cosmic book by the look of its faded, reddened cover. Even if we grow comfortable with the idea that this visitor was a strange, weathered comet at heart, another question lingers gently in the background, like an echo in a quiet room. If it was shaped by long ages of deep space, then where did that journey truly begin? From what distant shores in the galaxy did this small traveler set out before it ever crossed our path? Here, our view becomes hazy. We do not know its birthplace the way we know the orbits of our own planets. We only have rough estimates and careful guesses, like tracing ripples on a pond long after the stone has sunk. In the year 2018, astronomers tried to follow its track backward through space, rewinding its motion as best they could. Their calculations suggested that this object had likely been wandering the Milky Way for a very long time, perhaps hundreds of millions of years, before chance and geometry finally brought it near our Sunday. When they extended its path far into the past, they found that it came roughly from the direction of the constellation Lyra, near the bright star Vega. That does not mean Vega was its home. In fact, when they accounted for how stars move around the galaxy, they realized that Vega would not have been in that same place when the object might have passed nearby. The journey was simply too long. Over such timescales, even the stars themselves drift and swirl in their great orbits, changing the patterns of constellations that feel so fixed to us. By the time our traveler approached, the sky it had left behind no longer looked the same. As for how Oumuamua might have been flung out of whatever system it once called home, the leading ideas turned to gravity, that quiet architect of chaos in young planetary families. When stars are new and their surrounding disks are filled with growing planets, moons, and countless smaller bodies, everything jostles for space. Giant planets in particular act like bullies and guardians at once. Their strong gravity can nudge smaller icy bodies inward, outward, or sometimes all the way out of the system entirely. In our own solar system, this process likely happened on a vast scale. As Jupiter and the other gas giants formed and migrated, their gravity stirred the swarm of comets and planetesimals around them. Many were scattered into distant, elongated paths. Some were thrown so far out that they now form the distant, spherical reservoir we call the Oort cloud, a shell of icy remnants surrounding the sun at great distances. Others were ejected completely, sent sailing into interstellar space to become permanent wanderers. It is thought that our solar system alone may have cast off trillions of comet-like objects this way. If that can happen here, it can happen elsewhere. Oumuamua may have been one such piece of planetary shrapnel, chipped from the building blocks of another system and flung outward by the gravity of one or more giant planets acting as cosmic slingshots. A close pass near a massive gas giant could have given it a powerful kick, enough to break the grip of its parent star and send it drifting between the stars, free but forever homeless. There is even the possibility that its original home was not a single star at all, but a binary system, two suns orbiting a shared center. Some studies suggest that binary systems may be especially efficient at ejecting material during their early, turbulent years. With two sources of gravity pulling and tugging on young planets and small bodies, the dance becomes more complex, and the chances of flinging debris out into interstellar space may rise. In that kind of environment, a fragment like Oumuamua could easily be tossed away, another unnoticed casualty of planetary formation, beginning its long, solitary voyage. Another gentle thread in the tapestry of ideas imagines that Oumuamua might not have started as a small body at all, but as part of something larger. Perhaps it was once a piece of a distant, Pluto-like world, a frozen exoplanet with a surface rich in exotic ices, such as nitrogen. In that scenario, a violent collision could have shattered the larger body, sending nitrogen ice fragments into space. One such fragment, the theory goes, might eventually reach us. Because nitrogen ice can sublimate, turn from solid directly into gas under solar warming, this idea was also used to try to explain the mysterious acceleration, much as hydrogen sublimation had been invoked. It is a haunting picture, a shard of a shattered, distant world, still carrying the chemistry of a frozen surface from a star we will never visit. But when scientists examined the details, the nitrogen ice model faced its own obstacles, from the rarity of such material in sufficient amounts to the difficulty of reconciling the observations with the amount of nitrogen that would need to be lost. For many researchers, this explanation felt less likely than the hydrogen release scenario from more ordinary water ice shaped by cosmic rays. In a way, though, each of these origin stories, hydrogen, ice, nitrogen shards, water ice comets, feeds into a larger, calmer picture. They all rest on the same foundation, that interstellar objects, like Oumuamua, are probably not rare miracles, but common side effects of planet building. Whenever planets form, there is rubble. Whenever large bodies collide or migrate, there is debris. Over the lifetime of a galaxy, the number of ejected fragments builds and builds until the empty spaces between stars are not truly empty, but sprinkled with countless cold travelers. Estimates differ, and we cannot count them directly, but many models suggest there could be trillions upon trillions of such small exiles drifting through the Milky Way. Oumuamua, and later its successor, Borisov, a true interstellar comet observed in the year 2019, complete with a more familiar coma and tail, are likely just the first ones we have been lucky enough to notice with our current instruments. They are the tip of an invisible iceberg of wanderers that glide past unobserved all the time. By the moment our conversations and debates about Oumuamua's nature were in full swing, the object itself was already long gone. While we stayed behind, turning its brief visit over in our minds, it continued on its silent path away from the Sunday. Now, it is more than 40 astronomical units from our star, meaning it is over 40 times farther from the Sun than Earth is, out beyond the orbit of Pluto and still receding. Long ago, it crossed the distance of Jupiter's path. By the year 2019, it had gone past the orbit of Saturn as well. Between the years 2023 and 2025, it is likely slipping through the outer edge of the Kuiper Belt, that broad region extending from about 30 to 50 astronomical units, where countless icy bodies circle in the dim light. Beyond that thin, crowded ring waits a wider emptiness, a space where our sun becomes just another bright star against the black, no longer the center of a system but a small light among many. Oumuamua is on a one-way trajectory, heading back into that interstellar darkness. Its direction of travel now points roughly toward the constellation Pegasus. It will continue, slowly and steadily, along that line, carrying whatever story it holds with no one to read it. The speed it has now, relative to the Sun, is more than enough to keep it from ever being pulled back. The Sun's gravity has already done all the bending it can. From here on, the object will never return. From our point of view, this means something quietly final. Oumuamua is now too small, too dark, and too distant for any of our telescopes to see. No matter how large or sophisticated, their mirrors cannot collect enough light from that tiny speck to tell us anything more. The window of direct observation has closed. All that remains are the measurements we captured in those few short weeks, and the models and stories we build from them. There is a slightly sobering thought woven into this. If our observational capabilities had been a bit more advanced, if our surveys had been just a little more sensitive, we might have spotted Oumuamua earlier, perhaps while it was still approaching, rather than after it had already rounded the Sun and was speeding away. With enough warning, we could at least have watched it more closely, or, in a more ambitious dream, even dreamed of sending a small spacecraft out to meet it, to fly past and take a close look at this messenger from elsewhere. But reality was quieter and more humbling. The object was discovered only after it had already looped around the Sun, already accelerating outward on its way to the outer darkness. With the rockets and propulsion systems we have today, there was simply no way to catch up. It was like noticing a bird only after it had already taken flight over the horizon. By the time we realized how special it was already beyond our reach. That realization, though a little bittersweet, has also been a gentle wake-up call. It reminded scientists and engineers that the galaxy is not a still painting, but a living scene, with visitors passing through whether we are ready or not. If we want to do more than watch them disappear, we will need to be prepared in advance, with sharper eyes and faster, more agile spacecraft. Out of that quiet urgency has grown a new strategy to improve our surveys, refine our technologies, and think ahead, so that when the next interstellar traveler slips into our sky, we will not only notice it sooner, but perhaps be ready to reach out and meet it. In this way, Oumuamua's brief visit has gently nudged us toward preparing for the next interstellar visitor. That wake-up call did not just fade into the background. Almost as soon as Oumuamua's brief visit was announced, a small group of scientists and engineers began to wonder not just how to be ready for the next one, but whether it might be possible to turn around and chase this one. The thought sounded almost reckless at first, like deciding to run after a train that has already left the station. But the more they looked, the more they realized it might not be entirely impossible. From that quiet but daring question, a study effort took shape called Project Lyra, begun in the closing months of the year 2017 by the Initiative for Interstellar Studies. The heart of Project Lyra was simple: to ask, with clear eyes and careful math, whether a spacecraft launched with technology we either already have or could reasonably build soon might one day catch up to Oumuamua, or at least to objects like it. The challenge they chose to face was not a gentle one. When Oumuamua was detected, it was already heading away from the Sun at about 16 miles each second, which is roughly 5½ astronomical units per year. An astronomical unit is the average distance between Earth and the Sun, so you can imagine it steadily adding several Earth-Sun distances to its separation every year. That speed is faster than any probe humanity has ever launched. For comparison, Voyager 1, the fastest spacecraft humanity has managed to send into interstellar space so far, cruises at about 10½ miles each second relative to the Sunday. Even that record-breaking pace would leave a chaser slowly falling behind Oumuamua. To stand a chance of catching up, a new mission would need to go significantly faster than Voyager, perhaps by a wide margin. Despite how forbidding that sounds, the Project Lyra team found that, at least on paper, there are ways to do it. In early studies, published around the years 2018 and 2019, they explored trajectories that would let a spacecraft borrow as much energy as possible from gravity and from its own engines. One of the most promising ideas involved a daring solar obirth maneuver, sending the spacecraft extremely close to the Sun and then firing its engines at just the right moment, at perihelion, when it is moving fastest in the Sun's deep gravitational well. In this kind of maneuver, the Sun's gravity acts almost like a giant hill, and the engine burn at the very bottom of that hill can add more effective speed than the same burn would far away. The Parker Solar Probe, a real mission already flying, uses similarly close passes to study the Sun and gains enormous velocity as it dives within about 10 solar radii of the surface. Project Lyra imagined pushing that idea even further, using a close solar swoop not just to do science, but to fling a spacecraft outward at tremendous speed. Their calculations suggested that with the right approach, such a maneuver could boost a spacecraft to speeds above 45 miles each second relative to the Sun, fast enough to gradually close the gap and overtake Oumuamua in just a few decades. On interstellar scales, a few decades is almost quick. On human scales, it is the span of a career, long enough that some of the people who would launch the mission might not be the same ones who receive its final data. There was, of course, a catch. Swinging that close to the Sun is like flying near the mouth of a furnace. The heat load on the spacecraft would be extreme, demanding a very capable heat shield and careful design so that instruments and fuel remain safe. Timing would also be critical. To make full use of the geometry of Oumuamua's outward path, the optimal launch window for such a solar obirth maneuver turned out to be around the year 2021, only a few short years after the object's discovery. That was far too soon to design, build, test, and launch a brand new deep space mission. Rather than give up, the Project Lyra team simply turned their attention to later options. In a study from the year 2019, they traced out new opportunities, looking at launch windows in the late 2020s and the early 2030s. To their surprise and encouragement, they found that even if we waited 10 years or more, a carefully planned mission could still catch up to Oumuamua by the late 1940s of this century. They examined several specific years as promising starting points, including launches in 2028, 2030, and 2033, each with its own strategy. One scenario, for example, imagined a launch around 2028, followed by a sequence of planetary flybys to build speed and shape the trajectory. Perhaps a pass by Venus, then Earth, then another Earth swing by, all choreographed to deliver the spacecraft to Jupiter at just the right time. Once at Jupiter, the spacecraft could use the giant planet's gravity for another powerful slingshot, and possibly perform a high-energy engine burn near that encounter as well. Taken together, Jupiter's gravity and the engine's push would send the mission on a long, fast, outbound path designed to cross Oumuamua's track sometime in the 2050s. The beauty of this plan is that it avoids the need for a close solar dive and the harsh heat shield that would require. The Sun is kept at a respectful distance, and the spacecraft gains its speed more gently from planetary assists. The trade-off, of course, is time and fuel. A Jupiter-based strategy generally means a longer journey and significant propellant use for the final burn. It is a bit like choosing a route that is safer and more scenic, but takes more hours on the road and more fuel in the tank. Another trajectory the team considered involved a launch as early as 2026, with an even more finely tuned series of gravity assists. That path, however, assumed a timeline for building the spacecraft that is not realistic with current planning, so it has mostly remained a theoretical exercise meant to show what might be possible in principle. Stepping back from the individual options, the overall message from Project Lyra's analysis is surprisingly hopeful. If a mission were launched in the early 2030s, a rendezvous 15 to 20 years later appears to be within reach. That would place arrival sometime between about 2047 and 2050, wherever along its outbound path Oumuamua happens to be by then. For deep space exploration, those are relatively fast-track missions. New Horizons, for instance, took nearly a full decade to reach Pluto at about 30 astronomical units from the Sun, and here we are talking about going 2 to 3 times farther in roughly the same or slightly longer time, and at much higher closing speeds. Crucially, much of this does not demand miraculous new technology. The studies sketch out mission designs that rely on multi-stage rockets, gravity assists, and high-performance upper stages that are either already flying or under development. Launch vehicles like SpaceX's Falcon Heavy and NASA's Space Launch System are often mentioned as examples of the kind of heavy lift capability that could send such an interceptor on its way. Existing heat shield materials, similar to those already protecting Parker's solar probe, could be adapted for any close solar passes that might be needed. None of it is trivial, but none of it is magic. Most realistic mission concepts assume a one-way flyby rather than an extended rendezvous, especially at very high speeds. The spacecraft would rush past Oumuamua once, gather as much data as possible in that brief window, and then continue outward into the dark. Even so, that single close pass could transform our understanding. High-resolution images, direct measurements of composition, and detailed observations of its shape and rotation could answer questions that telescopes on Earth could only hint at. Project Lyra's curiosity did not stop with conventional chemical rockets. The team also looked into more advanced propulsion concepts that sit closer to the frontier between current engineering and the near future. One such idea is nuclear thermal propulsion. In that approach, a compact nuclear reactor heats the propellant, usually hydrogen, to very high temperatures before it is expelled through a nozzle. Because the reactor can heat the propellant more efficiently than chemical reactions alone, the rocket can achieve a higher specific impulse, meaning more push for the same amount of fuel. Studies suggest that nuclear thermal engines could roughly double the performance of today's chemical rockets. In a paper around the year 2021, researchers exploring this option for an Oumuamua interceptor found that it might not only shorten the flight time, but even open the door to an extremely ambitious possibility: a sample return mission. In that far more challenging scenario, the spacecraft would not only catch up to the interstellar object, but also collect material, perhaps dust or gas, and then turn around and bring it back to Earth for laboratory study. The technical hurdles are immense, but just thinking through the problem shows how much room there is for future missions to grow. Beyond nuclear options, the team let their imagination stretch a bit further into what might become possible if certain visionary projects are realized. One of the most intriguing concepts involves laser sail propulsion. This idea is related to the Breakthrough Starshot initiative, which envisions using powerful, ground-based or orbiting lasers to push ultralight spacecraft attached to thin, reflective sails, accelerating them to a few % of the speed of light. In the context of Oumuamua, Project Lyra's studies imagined a more modest version of that dream. If even a prototype laser array were built, one much smaller and less powerful than what Breakthrough Starshot ultimately aims for, and if a very lightweight probe with a reflective sail were designed to ride its beam, it could be accelerated to extraordinary speeds in a relatively short time. Under the right conditions, such a sailcraft might catch up to Oumuamua in only a few months of travel, or at the very least, in far fewer years than chemical or nuclear rockets would require. The lasers in this concept would act like a steady, powerful wind, pushing on the sail and gradually bringing the tiny spacecraft up to a velocity that would otherwise be unreachable. While this technology is not yet available, and many engineering and safety questions remain to be solved, Project Lyra's calculations show that even a smaller-scale laser system, far below the full Breakthrough Starshot vision, could still propel a probe fast enough to intercept the object within decades rather than centuries. All of these possibilities, from carefully choreographed gravity assists to closed solar dives, from nuclear engines to light-driven sails, share the same quiet wish: to transform a fleeting, mysterious dot of light into something we can truly see and touch with our instruments. Whether or not such a mission ever flies, the fact that people began sketching these paths almost as soon as Oumuamua appeared shows how deeply that little visitor stirred our curiosity and how far we are willing to imagine going just to follow a question into the dark. There was even a small, quiet smile hidden in the calculations. The Project Lyra team could not help but note that Professor Avi Loeb, who had once argued that catching up with Oumuamua was beyond our reach, now sits on the advisory board of the Breakthrough Starshot program. A system like the one Starshot imagines powerful lasers pushing feather-light sails to astonishing speeds could, at least in principle, send a swift little craft after that same elusive object in the future. The idea has its feet in theory and its head in the clouds, but it shows how the line between impossible and maybe, one day, can shift with time. For now, no space agency has formally approved a full interstellar interception mission. There is no spacecraft on the launch pad with Oumuamua's name written into its flight plan. Yet, the foundation has quietly been laid. Project Lyra's work offers a kind of architectural drawing for what such a mission might look like: how to design the spacecraft, which instruments it could carry to study, shape, composition, and activity, and even how to cope with the uncertainty of not knowing the object's exact position by the time we arrive. In a universe where the target is always moving and the journey takes decades, learning how to aim at a moving ghost is an achievement in itself. But the legacy of Oumuamua is not only sketched in equations and trajectory plots. Its brief visit also nudged us to build real, physical infrastructure so that the next interstellar messenger might be greeted while it is still on approach, rather than waved at in the rearview mirror. Over the coming years, several observatories and missions are poised to make us far less blind to such visitors. One of the most important is the Vera C. Rubin Observatory in Chile, expected to become fully operational by the end of the year 2025. Rubin is designed to do something very simple and very powerful: to look at the whole visible sky again and again, night after night, building up a moving, living map. Instead of staring deeply at one small patch, it will sweep its gaze across everything it can see, catching faint dots of light that shift their positions over time. Some of those dots will be new asteroids, some will be comets, and a few may be something stranger objects arriving from beyond our solar system. Computer simulations suggest that Rubin could detect many such interstellar wanderers. Depending on their sizes and orbits, it might find roughly one each year, or, if smaller bodies are included, perhaps dozens annually. Under optimistic conditions, some projections even hint at the possibility of discovering on the order of 70 interstellar objects per year. Even if reality turns out to be gentler and we only find one new interstellar traveler each year, that would still be a huge step forward compared to the current record of 2 known visitors in 6 years. More important than the exact count is the timing. Rubin will give us early warning. Early warning means we do not have to scramble after the fact. When a new object is discovered heading inward from the dark, astronomers can swing other telescopes toward it quickly, gathering more detailed data on its brightness, color, and behavior. Space agencies and private groups can discuss whether a rapid response mission is possible, even if that mission is small. The difference between seeing a traveler on the horizon and noticing it only when it is already at the door is the difference between planning a meeting and catching a glimpse. A few years after Rubin begins its sweeping survey, another piece of this new readiness will lift off. In the year 2029, the European Space Agency plans to launch a mission called Comet Interceptor. This spacecraft is unusual because it will leave Earth without a specific target in mind. Instead, it will travel to a gravitationally calm location known as the Sun-Earth Lagrange Point 2. A point in space, roughly 1 million miles from our planet, where the pull of the Sun and Earth balance just enough to let a spacecraft park and wait. There, Comet Interceptor will sit on standby, like a patient listener at the edge of a crowd. Its job is to be ready. If astronomers discover a long-period comet or a newly arrived interstellar object on a path that passes within reach, the spacecraft can leave its parking orbit and set off to meet it. The mission architecture includes a main craft and 2 smaller probe spacecraft. Near the target, these 3 will separate, flying different paths so they can capture the object from multiple angles at close range. Together, they will try to obtain the first detailed, up-close view of a truly pristine comet, one that has never been baked and altered by repeated passages near the Sun, or, in the most exciting case, a visitor from another star. Because Comet Interceptor is prepositioned, already in space and already free from Earth's gravity, it does not need to wait for a launch window after an object is discovered. That alone can save precious months or years. Speed is still a challenge, and any Oumuamua-like interception would depend on favorable timing and geometry. But the mission shows how we can change our posture from reactive to prepared. In a sense, Comet Interceptor is like a cosmic ambush predator waiting in the dark, not with hunger, but with curiosity, ready to spring toward any suitable prey that wanders close. Even if it never encounters an interstellar object, its very existence sets a precedent. It proves that we can build missions whose targets are not known in advance, missions designed to respond rapidly to whatever the universe chooses to send our way. Future spacecraft may follow a similar pattern, waiting quietly in deep space until awakened by the announcement of a new discovery. The fascination with Oumuamua also helped inspire something less traditional, a private scientific effort called the Galileo Project, led by Professor Avi Loeb, the same scientist who once openly suggested that Oumuamua might be a piece of alien technology. The Galileo Project does not assume that such objects are artificial, but it takes seriously the idea that we should be prepared to test that question with data rather than debate alone. The project focuses on two broad classes of phenomena. The first is unidentified aerial phenomena in Earth's atmosphere, unusual signals or objects seen in the sky that deserve careful, instrument-based study. The second is interstellar objects like Oumuamua, which could be of extraterrestrial origin or might simply be unusual natural bodies that stretch our understanding of what is possible. To study both, the Galileo team is developing a network of instruments, telescopes, cameras, and radar systems designed to monitor the sky in real time and record high-quality data whenever something odd appears. Their hope is that if another strange object sweeps into the solar system, whether it looks like a comet, an asteroid, or something entirely unexpected, they will be ready to track it quickly and to characterize it more deeply than we managed with Oumuamua. The project is also sketching out concepts for future space missions that could intercept such objects, complementing the ideas born from Project Lyra and other studies. Although the Galileo project is still in its early years, it has attracted attention and curiosity. Many astronomers remain cautious about claims of alien technology, preferring to exhaust natural explanations first. Yet even those who are skeptical about the more adventurous interpretations often acknowledge that the tools and methods being developed by Galileo, better sensors, more continuous monitoring, open data analysis, could be very valuable when the next interstellar visitor appears. Taken together, all of these efforts signal a gentle turning point. We are beginning to shift from being surprised and slightly startled by interstellar guests to preparing for them, almost as a host might quietly ready a room in case an old friend ever returns. We are still small, and our reach is still short compared to the size of the galaxy. But we are learning how to notice more, how to respond faster, and how to ask better questions when something from beyond our own star comes calling. The next time an object from another system glides through the inner solar system, we may be able to see it earlier, follow it more closely, and perhaps even send a spacecraft to meet it face to face. At the very least, we will be better equipped to decide what it is, and just as importantly, what it is not. The question is no longer whether more of these interstellar nomads exist. They do. The question is when we will see them, and how well we will be ready to listen to what they have to say. Each one, no matter how small or silent, carries a piece of information about worlds beyond our own, about how planets form, how they break, and what kinds of materials drift in the long dark between stars. In the meantime, we wait and watch, balancing humility with curiosity, feeling that mix of wonder and resolve that Oumuamua left behind. Somewhere out there, future messengers are already on their way, and we are learning, slowly and earnestly, to be ready for the next interstellar guest.